Welcome! Today, we're going to give your microcontroller its voice. We're diving deep into the UART peripheral on the PIC32 and totally demystifying it so you can get your projects talking. Let's get right into it.
Okay, so first things first, what in the world is a UART? The acronym stands for Universal Asynchronous Receiver Transmitter. It's basically a special piece of hardware inside your chip whose entire job is to send and receive data one single bit at a time. The two magic words here are full duplex, which just means it can talk and listen at the exact same time, and asynchronous, which is a fancy way of saying there's no shared heartbeat, no clock signal between the two devices.
I've always liked to think of the UART as the mouth and ears of your microcontroller. The PIC32? It's an incredibly powerful brain, right? But without a UART, it's kind of just stuck in its own head. This little module is what lets it talk to the outside world. I mean, everything from the GPS module, a Bluetooth radio, or even just your own computer's terminal.
So here's our game plan. We'll kick things off with what a UART can actually do. Then we'll jump into the key control registers you need to know. We'll figure out how to set the communication speed, see how data actually moves around, and then we get to the good stuff, a simple, practical checklist to get your first communication up and running. To wrap it all up, we'll take a quick peek at some of the more advanced features.
All right, let's start at the beginning. What exactly is this module capable of? What's it bringing to the table?
The UART on the PIC32 is surprisingly flexible. You can choose between 8 or 9-bit data, you can add parity for some basic error checking, and you can pick how many stop bits you need. But honestly, the real hero here, the absolute game changer, is that 4-level deep FIFO buffer. FIFO just means first in, first out. And having this little 4-byte waiting room for both sending and receiving is huge. It means the UART can catch incoming data even if your main processor is off doing something else. It's your safety net against losing data.
So to use any of those cool features, we've got to configure the hardware. And we do that using something called Special Function Registers, or SFRs. The best way to think about these is like the control panel for your UART. And this is where opening up a datasheet can feel, well, a little overwhelming. You see a massive list of registers, and it's easy to get lost. But here's the good news. To get a basic Hello World working, you really only need to get comfortable with 3 of them. We're just going to focus on UX mode, UXSTA, and UXBRG. First up is the UX mode register. Think of this as setting the ground rules for the conversation. Before any two devices can talk, they have to agree on the format, right? So this is where we decide, are we sending 8 bits of data or 9? Are we going to use parity for error checking? How many stop bits will we use to signal the end of a byte? All those fundamental rules get configured right here. Okay, next is USSTA, the status register. If UX mode was our setup panel, then USSTA is the dashboard of little status lights. It tells you exactly what's happening in real time. Is the transmit buffer full? The UTXBF flag will light up telling your code to just hold on for a second. Is there new data ready for you to read? The RxDA flag will tell you. And that OERR flag? That's your critical warning light. The data came in too fast and you might have missed something.
And last but definitely not least, we've got UXBRG. I just call it the speed dial. It's a 16-bit register, and its only job is to control the communication speed, what we call the baud rate. Getting the value for this register right is, well, it's absolutely critical. Let's spend a little more time on that speed dial. Getting the baud rate right is probably the most important part of the setup. If the speeds don't match between the two devices, all you're going to get is complete garbage. So how do we figure out the perfect value to put in there?
Well, the datasheet gives us this formula right here. The baud rate is based on your peripheral bus clock, that's the FPB, divided by 16 times whatever value is in your baud rate register plus 1. Now don't worry, you don't have to guess. We can just flip this formula around with a little algebra to solve for the UXBRG value that we actually need.
Okay, let's get our hands dirty with a real example, right? Let's say our goal is a super common speed, 9600 baud, and our chip's peripheral clock is running at 4 megahertz. We just plug those numbers into our rearranged formula, and we get 25.042. Now, obviously, you can't put a fraction into a hardware register, so we just round it down to the nearest whole number, which is 25. And here's the sanity check, the really important part. If we plug 25 back into the original formula, what do we get? We get 9615. Is that a problem? No way. That's an error of just 0.16%. It's well within what a UART can handle, and it's going to work perfectly. So we've set the rules of the conversation.
We've set the speed. Now, how does a byte of data actually make its way through the system? What's happening under the hood?
You can really see the two different paths here. To send something, your code just drops a byte into the UXTX-REG buffer. From there, the hardware automatically grabs it, loads it into the transmit shift register, and that register is what physically clocks the bits out, one by one, onto the wire. Receiving is just the opposite. Bits come in from the wire, they get collected in the receive shift register, and once a full byte has been assembled, bam, it gets moved over to the UXRX-REG buffer, where your code can finally read it.
So you might be asking, why do we need both a buffer and a shift register? Well, the shift register is the single worker B, the one doing the hard work of serializing the data. That 4-level buffer, that's its waiting room. This lets your processor drop off up to 4 bytes of data to be sent and then immediately go do something more important. On the flip side, it lets the hardware catch up to 4 incoming bytes before your code even has a chance to notice. It's all about efficiency and making sure you don't miss a single thing.
All right, that's enough theory. Let's put it all together into something you can actually use. Here's your step-by-step checklist for getting the UART up and running.
To send data out, it's just 5 simple steps. 1. Set your speed in UXBRG, using that calculation we just did. 2. Configure your format, the classic 8N1, 8 data bits, no parity, 1 stop bit, in UX mode. 3. You got to turn the whole module on by setting the ON bit in UX mode. 4. You have to specifically enable the transmitter by setting the UTXEN bit in UXSTA. And finally, step 5, just write your byte to UXTXREG. That's it. The hardware completely takes over from there.
And what about receiving? It's almost identical. The first 3 steps are exactly the same. Set the speed, set the format, turn the module on. But for step 4, you enable the receiver by setting the URXN bit. Then, in your main code loop, you just need to periodically check, or as we say poll, that RxDA status bit. As soon as you see that bit is set, you know there's fresh data waiting for you, and you just go and read it from the UXRX register. Simple as that. Now, everything we've just covered will handle, 95% of what you'll ever need to do. But it's really worth knowing that this little UART module has a lot more power hiding under the hood. For instance, it has full hardware flow control, which is great for preventing buffer overruns when you're sending tons of data really fast. There's a brilliant loopback mode that connects the transmitter directly to the receiver inside the chip. It's perfect for testing your code without needing any external hardware. There are also these advanced modes for creating multi-device networks using 9-bit addressing, a very clever auto baud detection feature, and even built-in support for the IRDA infrared protocol.
And there you have it, the PIC32 UART totally demystified. It really is that essential bridge between your code and the physical world. The registers give you the controls, the formulas give you the speed, and those buffers give you the reliability you need. So, I guess the only question left is, now that your chip can talk to the world, what are you going to build?